All right, let's dive into one of the biggest questions in tech right now. How on earth did AI learn to speak our language? We're going to break down the whole journey from seeing a jumble of letters to actually understanding and even generating text that sounds just like us. So let's jump right in.
I mean, think about it. You use AI all the time. You ask your phone for the weather, you get a quick summary from a chatbot, your email practically finishes your sentences for you. We're constantly talking to AI. But how does a machine, a piece of hardware, get the meaning behind what you're actually saying? Well, it all comes down to one fundamental challenge. See, computers don't speak English or Japanese or Spanish. They speak math. So the entire history of AI language models has really been a quest to find smarter and smarter ways to translate our messy, nuanced human language into cold, hard, structured numbers. Okay, so where does this journey even begin? Well, it starts with the very first attempt to solve this problem, a classic technique that honestly laid the groundwork for everything that came after. Step one is something called tokenization, and it's actually super simple. You just take a sentence, like, that is a cute dog, and you chop it up at every space. Each word becomes its own little piece or a token. It's kind of like breaking a wall down into a pile of individual bricks. So once you've broken all your sentences into these little token bricks, you gather up every single unique word you found. This big collection of unique words creates the model's dictionary, or what we call its vocabulary. This is basically the master list of all the words the AI officially knows. And here's the final step of that old school method. For any sentence, you just go through your entire vocabulary list and you count how many times each word shows up. So a sentence like, my cat is cute becomes a long string of numbers, a 1 for my, cat, is, and cute, and a 0 for pretty much everything else. It's called a bag of words because it literally throws grammar and word order out the window. It's just a jumbled bag with a simple count of each word inside. Now, bag of words was a start, right? But it had this massive, glaring flaw. By just counting words, it tossed out the single most important part of language, what the words actually mean. There's a line from our source material that just hits the nail on the head. To a bag of words model, the words king and queen are just words. It has no clue that they're related in any way. To the computer, king is as different from queen as it is from waffle. And that is a huge, huge problem. So, the solution, the big breakthrough, came in 2013 with something called Word2Vec. This introduced the idea of word embeddings. The goal here wasn't just to count words, but to create a string of numbers, a vector for each word that somehow captured its actual meaning. So how in the world do you teach a computer what a word means? The idea behind Word2Vec was brilliant. It's based on the phrase, you shall know a word by the company it keeps. So they trained a neural network on a ton of text with one simple job. Given two words, just predict how likely they are to show up near each other. By doing this millions and millions of times, the network starts to learn which words tend to hang out together. And the result is just incredible. You end up with this amazing multidimensional map of words. Words that mean similar things, like dog and puppy, end up grouped super close together in this map. And words that are totally unrelated, like apple and democracy, get pushed far, far apart. For the very first time, the numbers didn't just represent words, they represented relationships between them. Okay, so problem solved, right? We've figured out meaning. Well, not quite, because language is tricky. A single word can have totally different meanings depending on the words around it, the context. Yep, this is the classic example. If I say, I need to go to the bank to deposit a check, that's one meaning. But if I say, we sat on the river bank, that's completely different. A single static definition for the word bank just can't handle that. The model has to understand the entire sentence. So the next big leap forward was a new kind of model, the recurrent neural network, or RNN. Unlike the old bag of words, RNNs were built to read a sentence one word at a time, just like we do. This let them build up a kind of running memory, a sense of context as they moved through the sentence. Now, RNNs were a big improvement, but they still had a weak spot. They kind of gave every word in a sentence the same level of importance. The real breakthrough, the secret sauce, came when researchers figured out that, just like us, models need to learn how to focus. And that led to the attention mechanism. Honestly, the best way to think about it is like giving the AI a highlighter pen. As it's reading a sentence, it can highlight or pay more attention to the words that are most important for whatever it's trying to do. It learns to turn up the volume on the important stuff and tune out the noise.
At first, attention wasn't its own thing. It was an upgrade, bolted onto those RNNs to make them better. So check out this translation example. As the model is creating the Dutch translation for I love llamas, its attention mechanism lets it look back at the English sentence and focus specifically on the word llamas right before it spits out the Dutch word llamas. It's learning which input word matters most for the very next output word.
This idea of attention turned out to be so powerful, so revolutionary, that in 2017, researchers at Google published a paper with the legendary title, Attention is All You Need. It introduced a brand new architecture that completely threw out the old sequential RNNs and was built entirely around attention. And they called it the Transformer. Now, here's the game-changing part. By getting rid of that slow, one-word-at-a-time process of RNNs, the Transformer could look at all the words in a sentence at the exact same time. This meant it could be trained in parallel on gigantic datasets, which just massively sped up the whole process and let us build models that were way, way bigger than ever before. The core magic inside the Transformer is something called self-attention. As you can see here, older attention would look from one sentence to another, like from English to Dutch, but self-attention lets every single word in one sentence look at every other word in that same sentence. This is how a model figures out that in a sentence like, the cat chased the mouse because it was fast, the word it probably refers to the mouse, not the cat. It creates this incredibly rich, deep understanding of context. And this Transformer architecture, it is the foundation, the engine behind basically every major language AI you use today. It's what changed everything. So this new architecture split into two main families. On the left, you've got models like BERT. Think of these as amazing listeners. They read a whole block of text at once to get the full context, which is perfect for stuff like understanding a search query. Then on the right, you have models like GPT. Think of these as incredible storytellers. Their whole job is to predict the very next word, which makes them fantastic at generating new creative text. And this timeline just puts the whole story into perspective. You can see the slow, steady progress, bag of words, then Word2Vec in 2013, and then boom, the Transformer arrives in 2017, and you just see this explosion of innovation. BERT, GPT, GPT-ChatGPT, all within a handful of years. The Transformer was the spark that lit the fuse of the AI revolution we're living in right now. So we've gone from just counting words to building these complex, high-dimensional maps of meaning and context. We've taught machines our language by showing them statistical patterns across insane amounts of text. But it leaves us with one last, mind-bending question to think about. What happens when these models start seeing patterns and connections in our own language that we, the people who created it, have never even noticed? What are they going to teach us about ourselves?